The wheels pull back under the train. A few seconds later, the whole thing is floating about 4 inches above the track. No steel wheels, no normal engine pulling it forward, just magnetic force. And somehow, at 603 kilometers per hour, people inside can still sit there and read like it's a normal ride. That sounds like something from the future. But Japan has been working on this train for more than 60 years. And honestly, the speed is not even the craziest part. The real story is what Japan had to go through just to build the route. Around 86% of the railway runs through mountains. Engineers had to drill through unstable rock, deal with underground rivers, and build tunnels beneath stations that were still operating. Then one political decision stopped the entire project for 4 years. What started as a $9 billion idea grew into a $72 billion mega-project. Japan was not just trying to build a faster train, it was trying to build a completely new kind of railway through mountains that kept fighting back. So how did this project become so expensive? And after all these years, will Japan actually finish it before another country does? Back in 1964, Japan introduced the Shinkansen, and it completely changed the way people thought about high-speed rail. It was fast, it was reliable, and before long, it became one of the busiest rail lines in the world. But success created a problem. The Tokaido Shinkansen eventually reached its limit. During busy hours, trains were running almost one after another. There just wasn't much room to add more. The route itself wasn't helping either. It follows the coastline, winding around mountains instead of cutting through them. That means even if the trains got faster, the tracks could only do so much. Japan realized that simply upgrading the old line wasn't enough. If they wanted a real leap forward, they needed a completely different route. That's where the Chuo Shinkansen came in. Instead of going around the mountains, it would go straight through them. It sounded simple on paper. In reality, it would become one of the toughest engineering projects Japan had ever taken on. The idea actually started back in 1962. By 1977, a small test track in Miyazaki proved that magnetic levitation really worked. The train could float exactly as engineers had hoped. But making one train float on a test track was the easy part. Building an entire railway across some of Japan's hardest mountains was a completely different challenge. Before anyone was allowed to start digging, engineers spent 19 years studying the Southern Alps. They found fault lines, underground rivers, unstable rock, and mountains putting enormous pressure on any tunnel built beneath them. Even with the technology ready, nature wasn't making anything easy. After nearly 5 decades of research, planning, and testing, the project finally received approval in 2011. At that point, the train was ready. Now, the real challenge was convincing the mountains. The Yamanashi test track wasn't built just to see if the train could go fast. It was built to prove that the whole system could actually work together. Before crews dug the main tunnels, they drilled smaller pilot tunnels first. That gave them a chance to see what kind of rock was waiting ahead, instead of taking a blind risk. Once they knew what they were dealing with, the real work began. Every section of the guideway had to be installed with incredible precision. We're talking about millimeters over miles of track. Even a tiny mistake could become a serious problem at high speed. Then comes the part that completely changes how you think about trains. The motor isn't inside the train, it's built into the track. Both walls are filled with figure-8 coils that do 3 jobs at once. They lift the train, keep it centered, and push it forward. That means the railway itself becomes the engine. Before anyone could ride this train, thousands of coils, cables, sensors, power systems, and control equipment all had to work as one. At low speeds, the train still rides on rubber tires, but once it reaches about 160 kilometers per hour, the tires pull back automatically. The superconducting magnets take over, lifting the train about 4 inches off the guideway. From that moment on, there's no physical contact with the track. In 1997, the system reached 531 kilometers per hour. Later, hundreds of thousands of people rode the test train. Japan wasn't just trying to set a speed record. The real goal was to prove that this technology could do the same thing over and over again, safely, smoothly, and reliably. Because building one fast train is impressive, Building one that people trust enough to ride every day is a completely different challenge. Construction of the real railway finally began in 2014. The first section runs from Shinagawa to Nagoya, about 286 kilometers in total. What's surprising is that around 246 kilometers of it goes through tunnels. But the hardest part wasn't deep in the mountains, it started in the middle of Tokyo. The new station had to be built directly underneath one of the busiest Shinkansen stations in Japan. Trains above couldn't stop. Passengers couldn't be delayed. The city had to keep moving like nothing was happening. So, the engineers worked underground. They built massive concrete walls first, then started digging nearly 130 feet below the surface. Even getting the tunnel boring machines into the ground was a project by itself. They were simply too big to lower in one piece. Each machine had to be taken apart, lowered section by section, then rebuilt deep underground before it could even start drilling. These machines were enormous. Around 46 feet wide, nearly 500 feet long, and weighing close to 4,000 tons. As they pushed forward, they installed concrete tunnel rings behind them, almost non-stop. The excavated soil was carried away on conveyor belts to the surface, hour after hour. And the amazing part? Most people walking above had no idea any of this was happening. Cars kept driving, stores stayed open, bullet trains kept arriving on schedule. Life in Tokyo never slowed down. To me, that's one of the most impressive parts of this entire project. Not just building one of the world's most advanced railways, but doing it underneath one of the busiest cities on Earth without bringing that city to a stop. Digging under a city was hard. Digging through the mountains turned out to be even harder. On paper, the engineers already knew what kind of rock they would face. But once they actually started digging, the mountains had their own plans. Some of the rock was nearly 300 million years old. It was cracked, unpredictable, and nothing like the computer models had suggested. The cutting discs wore out much faster than expected. Tunnel walls became unstable. In some places, the pressure from the mountain was so strong it felt like the tunnel was being squeezed from every direction. That's when the original plan stopped working. Instead of relying on one tunneling method, the engineers had to change course. In the toughest sections, they switched to the new Austrian tunneling method, or NATM. It was slower, but it gave them more control. The crews moved forward one small section at a time. They drilled, they blasted, they cleared away the broken rock. Then they sprayed concrete, installed heavy steel supports, and anchored the tunnel deep into the mountain before moving ahead again. And that wasn't the only problem. Underground rivers kept showing up where nobody wanted them. Some had to be sealed, others had to be redirected. Sometimes, they were pumping out nearly 10,000 liters of water every single minute just to keep the work going. Even the rock they removed wasn't wasted. It was crushed and reused as part of the tunnel lining, while deep vertical shafts were built for ventilation and emergency access. Looking back, one thing becomes really clear. The engineers could decide where they wanted the railway to go, but the mountains decided how it would be built. They also decided how long it would take and how much it would eventually cost. You might think the hardest part was digging the tunnels. It wasn't. Once the tunnels were finished, an even bigger challenge began. Everything inside had to be installed with incredible precision, not inches, not even centimeters, millimeters. Every section of the guideway had to line up perfectly from one end to the other. At the speeds this train would travel, even the smallest mistake could become a serious problem. Then came the coils, hundreds of thousands of them. Each one had to be placed by hand in exactly the right position. Together, they form the motor that pushes the train forward. That's still one of the craziest parts of this project to me. The engine isn't really inside the train. The railway itself is the engine. The train carries powerful superconducting magnets, but they only work when they're cooled to about -269 degrees Celsius using liquid helium. At that temperature, the special niobium titanium wire inside the magnets loses almost all electrical resistance. That's what makes magnetic levitation possible. Every magnet has to be installed, cooled, checked, and tested before the next one goes in. Nothing gets skipped. The front of the train went through years of wind tunnel testing too. At 500 kilometers per hour, entering a tunnel creates a massive pressure wave. Without the right nose shape, passengers would hear loud pressure blasts every time the train entered a tunnel. Inside the cabin, though, you would hardly notice any of this. It feels calm, comfortable, almost like riding a normal train. More than 1,000 sensors are constantly watching every important system in real time. Most passengers will never see any of that technology. They won't see the magnets, they won't see the coils, they won't see the control center, making thousands of tiny adjustments every second. And honestly, that's probably the biggest sign the engineering worked. When something this complicated feels completely ordinary, you know an incredible amount of work is happening where nobody can see it. Building the train was only half the job. The other half was proving it could be trusted. The engineers didn't jump straight to top speed. They started slow, really slow. Every sensor was checked while the train was moving at little more than walking speed. Only after everything looked right did they move to 200, then 300, then 400, and eventually 500 kilometers per hour. Every step had to earn the next one. Of course, not everything went perfectly. During one high-speed test, a superconducting magnet suddenly lost its superconducting state. The safety system worked exactly as it was supposed to. The train stopped safely. Instead of treating it as a failure, the engineers treated it like valuable information. They traced the problem to vibration, redesigned the mounting system, and ran the test again. This time, it worked. Then they started asking even harder questions. What happens if an earthquake strikes while the train is traveling at full speed? Could the guideway actually keep the train safely in place? They built simulations to find out. They even tested two trains passing each other at a combined speed of more than 1,000 kilometers per hour. At those speeds, even the air between the trains becomes part of the engineering challenge. Then came the 21st of April 2015. The maglev reached 603 kilometers per hour and set a new world record. That's the number most people remember. But honestly, I think another number matters a lot more. Millions of test kilometers. Because that's where confidence comes from. Every problem became a lesson. Every lesson led to another improvement. And every improvement had to prove itself on the track all over again. To me, that's what really stands out about this project. Japan never assumed the design was good enough just because the math said it should work. They kept testing until the real world agreed. You'd probably expect a project like this to be delayed by broken machines or impossible engineering. But that's not what happened. The biggest setback came from something much simpler: water. One section of the railway had to pass through Shizuoka. People there were worried that tunneling could affect the groundwater, supplying hundreds of thousands of residents. It wasn't a small concern. If the water changed, entire communities could feel the impact. The engineers came up with a plan. They promised to return the groundwater collected during construction back into the river system. From a technical point of view, they believed the problem could be managed. But that wasn't enough. The local governor refused to approve the work. And just like that, one section of a massive railway project sat still for 4 years. Think about that for a second. Thousands of workers were ready. The technology was ready. Most of the route was moving forward. But one decision brought part of a $72 billion project to a halt. The original goal of opening in 2027 slowly slipped into the mid-2030s. At the same time, costs kept climbing: difficult geology, design changes, labor shortages, inflation. Everything added another layer to the final price tag. By then, what started as a $9 billion project had grown to roughly $72 billion. Things finally started moving again after the governor resigned in 2024. Survey work was approved, and construction crews were able to return. But I think this part of the story teaches the biggest lesson. You can solve engineering problems. You can build stronger machines. You can design for earthquakes, pressure, and extreme conditions. None of that guarantees a project will move forward, because in the end, people have to believe in it too. For a project this big, concrete and steel aren't always the hardest things to build. Sometimes, trust is. Even after all these years, the project still isn't finished. There's still plenty of work ahead. Because in Japan, building a railway isn't just about laying tracks. You have to prepare for earthquakes. That's why seismic sensors are installed all along the route. If an earthquake is detected, the trains can stop before the strongest shaking reaches the tracks. Even now, the engineers are still making changes. In some areas, groundwater levels shifted during construction, so tunnel linings had to be redesigned. Nothing is ever treated as good enough. Even the sections above ground have to meet the exact same precision as the tunnels. The train doesn't care whether it's crossing a bridge or running under a mountain. The standards stay the same. Then there's another challenge: finding enough skilled workers. Dozens of construction sites are still active, but Japan, like many countries, is dealing with a shortage of experienced workers. And while all of this is happening, the competition isn't standing still. China has already introduced its own 600-kilometer-per-hour maglev. That creates a new kind of pressure. Japan invented much of this technology. But there's still a real chance another country could put it into full commercial service first. Even so, Japan keeps improving the train while the railway is still under construction. Each new version is lighter, more efficient, less expensive to operate. The goal hasn't changed: turn a trip between Tokyo and Nagoya into a journey of about 40 minutes. Right now, thousands of tunnels, stations, guideways, substations, and maintenance facilities are already waiting. They're all built for one moment. The day this train finally becomes part of everyday life instead of just an incredible engineering project. Most people know this as the fastest train ever built. And that's true. But I don't think that's what makes this project special. To me, the real story is about refusing to quit when every new step creates another problem. The mountains forced the engineers to change how they built. Water forced them to earn public trust. Unexpected vibration forced them to redesign important parts of the train. Years of delays pushed the budget far beyond what anyone expected. Every obstacle challenged something they thought they already understood. And every time, they had to go back, fix it, and prove the solution actually worked. That's probably the biggest lesson I take away from this project. Building something extraordinary isn't just about having great technology. You also need the right geology, the right funding, the right safety systems, the right people, and maybe most importantly, the support of the communities you're building through. If even one of those pieces is missing, the entire project can slow down or stop, no matter how advanced the technology is. Japan has already shown the world that this train works. Now the final challenge isn't building a faster train. It's proving that an idea this ambitious can finally become part of everyday life.